Union Pacific 4884 steam locomotive 4014 is by far the largest and most powerful steam locomotive operating on the rails today. Big Boy's articulated design provides the power of two steam engines under the control of one crew. Is there any other steam locomotive that can be compared to the power of Big Boy? If so, what is it, and can it be documented, either in actual track testing against the 4014, or at least proven with historic data and testing? Atchison, Topeka and Santa Fe Steam Locomotive 5000, a 210-4 designed by Santa Fe's Mechanical Engineering Department in 1927 and built 14 years before 4014, takes the challenge. Before we get into the differences between 4014 and 5000, let's take a look back and see how the Big Boys were designed and built, and the changes to the railroad that had to be made to accommodate them. In 1936, the Union Pacific already had the 4664 Challengers on the road. They were performing well, but the demand for more freight speed for shippers was increasing in demand due to the country coming out of the Great Depression. In 1936, Otto Jabelman, vice president, was put in charge of the newly formed Department of Research and Mechanical Standards. The department had begun a modernization program to upgrade most of the system's locomotives, and were very busy when they were advised that Union Pacific was going to build a new locomotive capable of pulling 3,600 tons over the Wasatch Mountains unassisted. President Jeffers had the initial idea of building bigger power for the 1.14% grades of the Wasatch and made it top priority. It was early 1940, when Jeffers called a meeting with the Department of Research and Mechanical Standards, and told Jabelman and his staff to design and construct larger and more powerful Wasatch power. The preliminary design parameters and specifications for Big Boy was done on graph paper. They figured that for the new engine to be powerful enough to do the job, it would need to have 135,000 pounds tractive effort, with a factor of adhesion of 4. They started with the weight on the drivers, and then calculated horsepower and cylinder size with a boiler under 300 pounds per square inch. The obvious way to do it would be to enhance the 4664 Challenger design, already in successful service, by adding an additional driver to each articulated engine, and distributing the additional weight on the four-wheel leading and four-wheel trailing trucks. Consequently, the 4884. Since the design of the new locomotive was to be based on the 4664 Challenger, the American Locomotive Company was the natural choice for the builder. The top men from ALCO working on the Big Boy project were Robert B. McCall, Vice President, Joseph B. Ennis, Vice President, Engineering, and A. W. Bruce, assistant to Mr. Ennis, who was also a noted authority on steam design and history. The Union Pacific's Department of Research and Mechanical Standards, headed by Otto Jabelman, and ALCO worked together in 4 design teams. The Union Pacific and the builder provided specifications and design details, but most of the time the road's desires were implemented. The design and building of the big boy only took about a year. 6 months were spent on design, and 6 months to build. They were not only designing the new locomotives for power, but also wanted to over-design the rotating parts of the engine. They designed the new 4884 to be capable of 80 mph speed. Not that they thought they would ever haul freight anywhere near that speed, but wanted to eliminate all possibility of rod breakage, by over-designing the running gear. After the final design had been completed, and they were ready to start construction, the Union Pacific ordered 20 big boys at once, at a cost of $265,174 each. They had calculated that 20 units would allow them to be able to handle all the manifest and normal fruit block movements between Ogden and Green River. It would also cover the normal factor of 2 locomotives in the shop at any given time. The chief engineer's office began checking clearances for the new engines all the way from Council Bluffs to Ogden. They soon realized that the new locomotives would only have a clearance of 7 7/8 inches between 2 engines passing on a double-track 10-degree curve. The lateral motion devices on the new units allowed for a 5/8 movement in the drivers, which would allow the front end to swing out even further, reducing the clearance to only 5.5 inches. This information was assimilated, and the necessary adjustments to the design of the locomotive was changed immediately. This included a reduction in the width of the running boards from 20 inches down to 15. Then in April, it was noticed that the boiler at running board height would not clear a 12-foot wide load on double-track 10-degree curves, with the standard 13-foot track centers. Consequently, the summer of 1941 was terribly busy for the chief engineer's office, and track gangs who had to realign curves between Ogden and Green River. Most of the time, the curves could be jacked up and moved over about 4 feet. Some, however, had to be completely realigned because they had varying degrees of curvature. Sidings and curves leading in and out of passing tracks also had to be realigned. The siding at Gateway could not be realigned, due to insufficient room, and was eliminated completely. The big boy's weight required new 131-pound rail to be laid over most of the route between Ogden and the summit. Getting everything ready for the big boy to be able to operate on the territory it had been designed for was taking a lot of extra work. This is in stark contrast to the design and development of 5000, who was able to travel the entire Santa Fe system, without curve realignments and siding and track center modifications. Downtown Chicago was about the only place 5000 could not go because of tight clearances. While being constructed, Union Pacific personnel traveled to and from the builder, and some of Alco's people came to Omaha to make sure that everything was proceeding smoothly. Some of UP's inspectors lived for 6 to 9 months in apartments and hotel rooms in Schenectady, while the units were being erected. Some did not make it back to Omaha until after the last unit was delivered. On September 5, 1941, the Union Pacific officially accepted the delivery of Engine 4000 at the Omaha shops at 6 p.m. A large crew worked around the clock for more than a day, connecting the rods and other modifications, so the new engine could enter service. The 4014's massive dimensions are even greater than the 5000, but what is the difference in the hauling power of the 4014 and 5000? At first this question seems easy to answer. The published tractive effort of the 5000 is 93,000 pounds, and the 4014's tractive effort is listed at 135,375. So, the answer is that the 4014 is 31.4% more powerful than the 5000, but we will soon discover this is not true. Shown here is a comparison chart of the 5000 and 4014's principal dimensions and specifications as originally built. It is interesting to note that the chart shows that 5000 exceeds the 4014 in some key areas such as piston diameter and stroke, combined heating surface, superheating square feet, driving wheel diameter, and firebox width. Further investigation into the 93,000 pounds tractive effort listed by Santa Fe Railway for the 5,000 revealed that it was calculated by simply taking 25% of the weight of the drivers. The weight on 5,000's drivers during her testing in 1931 was 372,000 pounds. 25% of 372,000 equals 93,000. This method was used by locomotive designers for estimating how much tractive effort a new design for a locomotive will have before it is built. It is not normally used to calculate a steam locomotive's tractive effort after construction. Most, if not all, of the steam locomotives in the United States had their tractive effort calculated using the Standard Association of American Railroads formula. The Santa Fe Railway had always used this formula until the 5,000 came out. They decided to use the 25% of driving wheel weight method instead of the Association of American Railroads formula. Why? The most logical reason is that the Santa Fe Railway was very conservative in their published data of tractive effort output for their equipment. They may have wanted a very safe figure for their trainmasters to select motive power for their district. The low figures would give them a very safe margin of error for assigning engines to trains. The Santa Fe used the 93,000 pound figure for all the 5,000 classes. The Association of American Railroads formula would have calculated 5,000's tractive effort at 113,000 pounds. Using the Association of American Railroads formula on the big boys, the tractive effort comes out to 135,000 pounds. Obviously, the Union Pacific used the formula to rate the big boy. The most accurate way to measure the tractive effort of any locomotive is with a dynamometer car, coupled into the train consist directly behind the locomotive's tender during a test run. Fortunately, we have acquired a copy of Report of Test 87249 of Locomotive 5000, showing her performance in freight service between Clovis and Belen, New Mexico in the summer of 1931. Special thanks to Craig Ordna, archivist of the Railroad and Heritage Museum, and the late Larry E. Brasher, who found the test and provided a copy for our research. The Report of Test 87249 is very thorough with lots of detail about the 5000's performance during 12 test runs on the 1st and 2nd districts of the Pecos Division. The object of this test was to determine the performance of Locomotive 5000 in freight service on the Pecos Division between Clovis and Belen. Here is how Dynamometer Car 29 evaluated 5000. Locomotive 5000 was received from the Baldwin Locomotive Works about December 15, 1930 and was placed in service the last week of that month at Clovis, New Mexico. This locomotive is designed with a greater ratio of boiler capacity to tractive power than is generally used. It is of the 210-4 type, carries 300 pounds boiler pressure, and is limited to 60% maximum cutoff. The main steam valves have 3-inch steam lap, 1/8 of an inch exhaust lap and maximum travel of 9 7/32 inches forward and 9 3/8 inches backward motion. Special equipment is as follows: Type E superheater, American multiple throttle, Alesco feed water heater, located on top of the smoke arch, Alesco CF pump, located on left side under cab deck and back of left trailer wheels. Standard stoker, wall start valve gear, Rogonnet reversing gear, Chapman landing auxiliary starting valves, Chicago mechanical lubricator, Nicholson thermic siphons in the firebox and one in the combustion chamber. 2 8.5-inch cross-compound air pumps, located on the pilot deck. Round hole table grates composed of 6 sections, shaken by hand lever, Muchnick sectional bull ring packing, with 3 sets of bronze rings on each piston head. The engine truck has outside journal bearings. The main and side rods are of the Lima type. The exhaust nozzles were increased from 3 3/4 to 3 7/8 inches diameter before starting on run 9, and before starting on run 10 an extension 14 inches long was placed over the stack. Santa Fe Dynamometer Car 29 was used to record drawbar pull, speed, rate of firing, rate at which water was supplied to the boiler, air brake operations, and time of passing stations, starting and stopping. Cab readings included boiler pressure, steam chest pressure, back pressure, position of throttle, reverse lever, temperature of superheated steam entering the valves, temperature of smokebox gases, and the readings of a valve pilot, a device applied by the Valve Pilot Corporation, which kept a record of the speed and position of the reverse gear. Crosby steam engine indicators were used to determine the steam distribution in the cylinders, and 2 4-inch hot water meters were used, one on the suction line of the pump, the other on the injector to record the amount of water delivered by either, which was recorded on the chronograph chart. Check readings were also made by means of gauge boards on the tender. An electric contact was attached to the stoker conveyor which recorded the revolutions. Temperatures were taken of the feed water before entering and after leaving the feed water heater. The amount of cinders thrown from the stack was determined by a catcher in the form of a sector, placed over the stack covering about 1.95% of the area, diverting the cinders caught into a container. From the amount of cinders caught, the total amount discharged was determined. The coal consumption was determined by leveling the top at the beginning of a trip, filling to the same level at the end, and taking the weight shown by the coal chute scales. The test was made on the 1st and 2nd districts of the Pecos Division between Clovis and Belen, New Mexico. The ruling grade is 0.6% westbound. Eastbound it is 1.27% from Belen to Mountain Air, and 0.6% Mountain Air to Clovis. Helpers are used on the 1.27% grade, though Locomotive 5000 was used alone on run 10. The locomotive was handled by pool crews which changed at Vaughan going either direction. The road foreman of engines, or the fuel supervisor accompanied all trips to assure uniform handling, and 5000 was operated with wide open throttle where conditions permitted. In preparing the locomotive for test, in addition to applying test apparatus, all driving wheels were dropped, lateral was taken up, main floating bushing renewed, number 1 and number 4 knuckle pin bushings applied to right side, about 300 stay bolts in firebox driven, and valve pilot applied. The indicated tractive effort chart from Dynamometer Car 29 during the 1931 testing of 5000 shows an incredible 132,500 pounds tractive effort. The summary of all the test data on 5000 gives us an average of the indicated tractive effort of 111,840 pounds, and the American Association of Railroads formula calculates 5000's tractive effort to be 113,000 pounds. So, we have 3 possible tractive efforts for 5000. 93,000, 113,000 and 132,500. Which one is the most accurate? One thing is sure, the published 93,000 tractive effort for Locomotive 5000 is low. The indicated tractive effort of 132,500 pounds from the diagram is probably high since indicated tractive effort does not consider losses in the running gear. The diagram shows an average of 111,840, which should be the most accurate, since it is the average of all the 1931 test runs. Dynamometer tests on the 5001 and 5011 class show a tractive effort of 105,200. The Association of American Railroads formula would have given the 5001 and 5011s a tractive effort of 109,000. The Association of American Railroads formula is 3.5% higher than the dynamometer test. If we take the 5000's Association of American Railroads figure of 113,000, and reduce it by 3.5%, we have a tractive effort of 109,045. The 5000, however, was rated for higher tonnage on the Pecos division than the 5001 and 5011 class. 5000 was rated for 3,200 tons, the 5001 and 5011 class were rated for 3,000 tons. This is due to the larger drivers on the later class engines. The 5001 and 5011 class had 74-inch drivers, 5 inches larger than the 5000. The smaller drivers gave 5000 the ability to take 6.25% more tonnage up the 1.27% ruling grade of the Pecos division. With such a detailed dynamometer test of 5000 in hand, all we need now is a dynamometer test of the 4014. We searched the RAPS archives and the internet for possible dynamometer tests of the 4014, or any big boy for that matter. We were amazed to find not only a dynamometer test of 4014, but two other big boys had been tested, 4004 and 4016. The Union Pacific Railroad designed 4014 from the drawing board to be able to haul 3,600 tons up the 1.14% grade of the Wasatch Mountains unassisted at the speed of 18 miles per hour. When the big boys were delivered, this was immediately tried to verify the success of their design. The dynamometer test runs on the big boys were conducted between Ogden, Utah and Evanston, Wyoming, in the spring of 1943. What we need now is to find the test run of 5000 that matched the closest conditions of the 4014 tests. We must have at least two tests, one of 5000 and one of 4014 that were done under similar conditions of tonnage, grade, and weather, with a dynamometer car. This will give us the best possible chance of comparing 5000 and 4014 with actual data from their test runs. During the time of these tests, 5000 was 100% friction bearings. 4014, on the other hand, was all roller bearing. We are not sure what difference this would have made, but it is bound to have some effect. Both locomotives were operated under coal fuel, on steep grades, during clear dry weather conditions. These tests are the best comparisons we have of the two great engines. The test runs show that 5000 is remarkably close to 4014 power. Run number 10 was unique from the other 11 tests on 5000, because it was the only run where 5000 was tested on the 1.27% grade without a helper, and was recorded by dynamometer car 29 between Belen and Vaughan, which was fairly close to the conditions under which 4014 was tested. During this run, 5000 hauled 3,224 tons unassisted up the 1.27% grade to mountain air with an average speed of 25.5 miles per hour. The 1.27% grade was 10.3% steeper than the 1.14% grade where 4014 was tested. Simple math will show that, all things being equal, 5000 running on a 1.14% grade would be able to haul 3,556 tons. The difference between 3,556 tons and 3,600 tons is only 1.3%. 1.3% of 3,600 equals 46.8 tons. At the time a loaded boxcar was 50 tons. This brings the difference in the hauling ability of 5,014's design tonnage rating to be less than one loaded boxcar. It is surprising to learn that 5,000 was this close to 4014's design power. Tractive effort calculations, no matter what method is used, can be very misleading. The 132,500 pounds tractive effort figure calculated by Dynamometer Car 29 is the highest tractive effort figure for 5,000. The 132,500 figure is only 1.9% lower than 4014's 135,000 published figure. How can this be possible? 4014's advantages. 156 tons heavier than the 5,000, 2 steam engines, 68-inch driving wheels, twice as many piston cylinders and side rods. Firebox is 6 feet longer than 5,000, 540,000 pounds on the driving wheels, compared to 5,000's 372,000 pounds. Roller bearings on all axles and needle bearings on valve gear. Let's look at the dynamometer test run of 4014 and see how it compares to 5,000. Note: A. 5,000 would pull 3,556 tons if on 1.14% grade. This makes the difference in tonnage performance between 5,000 and 4014, 1.23% in favor of 4014. B. 5,000 used 41.1% less pounds of water per hour running time than 4,014 even though it was pulling a 10.3% steeper ruling grade. C. 5,000 used 64.1% less pounds of coal per hour running time than 4,014 even though it was pulling a 10.3% steeper ruling grade. The 4014 should have every advantage, and theoretically far exceed Madam Queen's hauling ability. But it does not. Why? The main reason is weight on the drivers. 4014 has 540,000 pounds on the drivers or 31.2% more weight on the driving wheels than Madam Queen. However, the 4014 also has more axles. 3 more than Madam Queen. 4014's 540,000 pounds on the drivers is spread out over 8 axles, giving each axle 67,500 pounds. Madam Queen, on the other hand, has 372,000 spread over 5 axles or an average of 74,400 pounds per axle. Weight on the axles is a key factor in the engine's ability to haul tonnage. Let's take a look at the importance of weight per axle. First, a few definitions need to be given. Definition of tractive effort. Tractive effort is the force of the driving wheel that is applied to the rail. Definition of adhesion. The ratio of tractive effort to the weight on the drivers. The amount of tractive effort determined from the Association of American Railroads formula, and even dynamometer tests show the tractive effort that can be developed, and is independent of locomotive weight or driving axle weight. What really counts, is the tractive effort that can be utilized. Utilized tractive effort is dependent on locomotive weight, especially driving axle weight. Utilized tractive effort is where 5,000 really shines. We pointed out earlier that the 4014 has an average of 67,500 pounds of weight on each of her 8 driving axles. 5,000 has an average of 74,400 pounds of weight on each of her 5 driving axles. 5,000's driving axle weight is more concentrated, due to fewer drivers, and therefore 5,000 is able to come close to 4014's performance, even though the 4014 seems to have every other advantage in her favor. 4014 has less tonnage hauling capacity than it should, given the engine's tremendous weight. The articulated design, having 8 driving axles, ultimately works against its tonnage hauling efficiency. Now we need to consider piston thrust. Piston back thrust is calculated by taking the area of the piston in square inches, multiplied by the boiler pressure. 4014 piston back thrust equals 132,904. 5,000 piston back thrust equals 212,058. 5,000 has 37.3% more piston back thrust than 4014. Only the 5001 and 5011 class locomotives had higher piston back thrust than 5000. The 5001-5011 class engines had 219,126 pounds back thrust, due to the 10-pound increase in boiler pressure to 310 pounds. 5000's tremendous piston back thrust power was delivered to her driving wheels, that had much more weight per axle than 4014. This gave 5000 great tonnage hauling capacity. Another important factor is valve chest pressure and back pressure. All steam locomotives lose some boiler pressure by the time the steam works its way to the cylinders. The steam passing through the superheaters, throttle, valves, etc. will reduce the energy available from the steam. The length of the steam delivery pipes, and how well they are insulated is also a factor. The superheater was designed to help overcome this pressure loss by heating the steam up to 700 plus degrees Fahrenheit, so that full pressure would still be available by the time it reached the pistons. 5000's average valve chest pressure on the 12 test runs conducted in 1931 was 281 or 19 pounds below boiler pressure. Her back pressure averaged 12.4 pounds. 4014 had a back pressure of 17 pounds. This reduces the 300 pounds boiler pressure down to 281 before the loss from long multiple turning steam delivery pipes was factored in. On 5000, the steam travels directly from the superheater straight down the steam delivery pipes and directly into the cylinders, about 6 to 8 feet. This is a very direct and short route for the steam to take. The shorter and straighter the distance to the cylinders, the less pressure loss. 4014, due to its articulated design, has long-running steam passages to get the steam to the cylinders. The steam coming out of the superheater not only had to travel the normal distance to get out of the boiler, but also through long pipes up to 20 feet in length which ran just underneath the catwalk to the rear engine. The front engine steam also has a long delivery pipe. Wolf Fengeler, RAP's senior mechanical engineer, had this to say about the big boy's steam flow. The real source of pressure loss in this case is the various bends, changes in flow area, and wall friction that the steam encounters during its journey from the boiler to the cylinder. With long pipes, and many bends, the 4014 has lots of sources of pressure drop. The lack of insulation will serve mostly to decrease the temperature of the steam and thus its energy content. The dynamometer data shows that the 4014 was already down to 281 pounds valve chest pressure after deducting 19 pounds of back pressure. The long steam passages would lower the valve chest pressure even further. Another potential threat to 4014's ability to produce steam pressure efficiently is its system to heat the feedwater. 5000 used the Alesco feedwater heater, but the big boys used a much less efficient exhaust steam injector system instead. The exhaust steam injector system was often referred to as a poor man's feedwater heater. It had a tricky starting sequence and many engine crews would avoid their use altogether. Having a less efficient system to preheat the feedwater would make it difficult to keep the steam up. We don't understand why Union Pacific, which has a reputation of buying the best of everything, didn't install an Alesco or Worthington feedwater heater on their finest motive power. It is unknown if Union Pacific corrected this problem when they restored 4014. In summary, We have found that both locomotives are magnificent engines and are among America's greatest locomotives. Both certainly deserve to be restored to steam operation, and will be a delight for all who are fortunate enough to witness their magnificent power and size under full steam. The most important thing that our research has revealed is that comparing locomotives by tractive effort and horsepower does not reveal the actual tonnage hauling ability of a locomotive. The dynamometer tests proved that although 4014 had every advantage in tractive effort, horsepower and on-paper statistics, 5000 could perform tonnage hauling ability up the mountain awfully close to 4014.